アメリカ西海岸の名門カリフォルニア大学バークレー校。自由な校風で知られるこの大学に今全米から注目される一人の研究者がいます。旧ソビエト出身の気鋭の数学者エドワード・フレンケル教授です。
フレンケル教授が挑んでいるのはラングランズプログラムと呼ばれる数学界最大のミステリーの一つ。教授の最終目標は整数や分数など数とは何かを研究する数論。図形の形や性質を調べる幾何学。そして複雑な関数を読み解く解析学など、一見互いに無関係だと考えられてきた数学のさまざまな分野に実はミステリアスな深いつながりがあることを証明しようという壮大なチャレンジです。もしこのラングランズプログラムが完成し、さらに数学の全ての分野が地続きであることが示せれば、数学者たちを悩ませ続ける数々の難問が解決する可能性があるといいます。
The Langlands Program is a set of ideas about how these pieces fit together, how they should fit together, which we still don't know, for which we still don't know the answer.
それだけではありません。フレンケル教授は抽象的な世界を描く数学と私たちが暮らす現実世界を研究する物理学の間にも驚くべきつながりがあると予想しています。数学の最先端理論を突き詰めていけば、この宇宙を支配する物理法則が次々と姿を現すのではないかというのです。
フレンケル教授は今回一般の学生から数学の専門家までを集めた全4回の特別講義を行いました。フェルマーの最終定理、ガロア群、そしてスーパーストリング理論。最先端の世界が次々と登場。学校では決して教えられない美しくて楽しい数学の世界が大展開します。
In these lectures, I will talk about the beauty of mathematics. What is mathematics really about? Well, it turns out that this is a subject which is much bigger and much more sophisticated and fascinating than anything we study at school. I will tell you some things which will blow your mind. I will talk in this lecture about the continents of mathematics, such as number theory, geometry, harmonic analysis, and I will talk about the grand unified theory of mathematics, the so-called Langlands Program, which I think is one of the most important developments in the subject in the last 50 years. Hello, how are you guys doing? Good? Well, and I already feel excited, and I hope you will too. So, which sometimes, it's not the first word which comes to mind when we talk about mathematics, the word excited or exciting. But I think that that's because of the way we usually present mathematics to others, to non-mathematicians. We mathematicians, of course, know how exciting and fascinating the subject is. And my goal is to convey to you that excitement and that knowledge, in such a great opportunity, really, to be able to do that. So, the difference between painting the fence and the paintings of the great masters. Yes, in both cases, paint is involved, but, to very different ends. And I feel that sometimes the way mathematics is presented to us at school is more like painting the fence, teaching us how to paint the fence. And if so, then of course we don't feel so motivated, because people say, well, why do I need to learn this? If I ever need it, done to my fence, I will just hire someone to paint the fence for me, without realizing that actually there is so much more. And so, in fact, what I would like to tell you in these lectures, what I would like to convince you of, would like to present you, is the idea that mathematics is more like the paintings of the great masters, like this Starry Night by Van Gogh. that in fact mathematics is a hidden parallel universe full of elegance and beauty, which is intricately intertwined with our world. So let's see. I will talk about the Langlands Program, this fascinating subject which was developed in the last 50 years, and I would say one of the most exciting ideas in mathematics to come out in the last 50 years. But I will also talk about other areas of math and kind of just to give you a feel, an idea of what mathematics is really about. Well, let me start with the great quote from Galileo, who said that the book of nature is written in the language of mathematics, and the symbols in it are triangles, circles, and other geometrical objects, without which we wouldn't be able to understand a single word in it. Without which, he says, we would be left wandering in a dark labyrinth. So mathematics is a language of nature, but it's not just at the service of science. It's not just at the service of physics, for example. Physical theories get updated, get discarded. Newton came up with the theory of gravity, which for centuries was considered as the most important and the final word on the subject. And then Einstein came and told us that actually the story was much more complex and much more fascinating in many ways. So the theory got updated. And of course, there is no reason to believe that Einstein's theory is the last word. And perhaps some of you will come up with some theories, some ideas which will update Einstein. So that's kind of something we expect from theories of science. But mathematics is different. Mathematics is different. And the question I want to ask is whether mathematics is actually a kind of a universal language which does not get updated, which is timeless and persistent and necessary. And to illustrate that point, let me talk about the great novel of Leo Tolstoy, my compatriot, because obviously I'm Russian. And, great novel. But if Tolstoy didn't live or didn't write Anna Karenina, there is no reason to believe that someone else would have written the same novel, right? Now compare that with mathematics. Pythagoras' theorem is, of course, one of the landmark achievements of mathematics, going back 2,500 years ago to Pythagoras, about right triangles, triangles which have one of the angles equal to being 90 degrees, that the sum of the squares of the legs is the square of the hypotenuse. If Pythagoras had not lived, or did not discover Pythagoras' theorem, we would still have it. Someone else would have discovered it. And in fact, many have. In fact, we know now that perhaps the theorem was already known in other parts of the world, to the Babylonians, Indians, Chinese. It's not clear that Pythagoras was the first one. I would say it's discovered, perhaps every week in our classrooms by some kids who are, playing with the triangles. So you see, this is something which was discovered by Pythagoras 2,500 years ago, but we surely don't expect it to be updated. We don't expect next year it to read a squared plus b squared equals c cubed, right? It will still be c squared. So what is it about mathematical ideas which make them so special? And some have speculated that, in fact, they live, mathematical ideas and concepts and theorems, they live in a world of its own, in a world quite apart from the physical world around us. And these ideas go back to the Greek philosopher Plato, so sometimes it's referred to Platonic ideas, Platonic world of mathematical ideas. And so the question, which of course the jury is still out, we don't know. And that's the beauty of mathematics. It's one of the questions that we're still pondering, we're still trying to understand, is do we discover mathematics or do we invent it? Or perhaps, maybe, let's try to be a little bit more concrete. Let me rephrase it. If we ever meet aliens, and well, since we live in Berkeley, some of you may have already done that. But if we ever meet aliens, should we expect that the aliens will have the same math? Or would it be different? Now, usually when we talk about aliens, we imagine some creatures like this. But it doesn't have to be this way. An alien intelligence could have a totally different shape. Nowadays, of course, this is not so much a theoretical question as it becomes more and more practical question, because, in fact, scientists now find more and more planets on the sort of outskirts of our galaxy and other galaxies, which seem to be capable of supporting life, just like Earth. So it is kind of an interesting question, not just as a theoretical, but as a practical question. But that intelligence could take a different shape. You may have seen the famous film by Andrei Tarkovsky, another Russian reference, called Solaris, based on a book by Stanislav Lem, in which the whole planet was intelligent. And so some mathematicians have suggested that a Solaris-like intelligence would not be able to discover numbers. Because why? How would the Solaris intelligence discover numbers? Because there's only one. Here we can count people, 1, 2, 3, 4, 5, 6, and so on, right? We are used to discovering things by counting, discovering numbers by counting. But a Solaris is only one. So some people suggested, well, perhaps such an intelligence would have a different approach to mathematics in the first place. What I would like to argue is that's not necessarily the case, that actually there would be a way for Solaris-like intelligence to discover numbers. So you see, it looks so appetizing that I actually decided to bring the real ones. I didn't want to torture you with that picture. I wanted actually you experience them. You see, but there is a problem with this, because you see, they all look a little different, like this one is a bit more red than this one, and so on. So when we say that they are the same, I say 1, 2, and so on, it's a bit of a cheating, if you think about it. And in fact, if you teach kids this thing, they will tell you, why are you counting them as if they were the same? And they're not the same. You can have some. So in mathematics, actually, there is another way to discover numbers. There is another way to discover numbers, whole numbers. We call them whole numbers, 1, 2, 3, 4, 5, and so on, right? We call them whole numbers, or sometimes they're called natural numbers. There is another way. And the way we discover them is by what we call winding, which actually is very easy to explain. And my dentist would be really proud, because he's always complaining that I don't do enough flossing, which is true. But I'm trying to get better at this, so I'm actually going to do it right now. No, I'm joking. But I'm just going to... It may not be the best place. But, okay, but I just want to show you something. You see, when we have a floss, okay? When we have a floss, and then I try to wrap it around my finger like this. So what do? It's 1, 2, 3, 4, right? I'm actually discovering numbers by wrapping this string, that floss, around my finger. And in fact, it's better than strawberries, because there is no such thing as a -1 strawberry. At least I've never seen it. I bet it tastes awful. But with the floss, it's very easy to get negative numbers. You just wrap the floss around in the opposite direction, you see. So this way, you actually discover not just positive whole numbers, 1, 2, 3, 4, 5, but you discover all integers, all whole numbers, positive and negative. And there's a picture which illustrates that, you see. Now, so this is very clear, right? But you can also think of this as a circle wrapping onto itself. So you see, you have a circle, and you can think of the circle wrapping onto itself. So if you have an intelligence in the form of a circle or a disk, that would be a sure way for it to discover whole numbers, simply by realizing that it can wrap onto itself. Now, what is less obvious to a non-mathematician is the fact that a sphere can actually do the same. A sphere can also wrap onto itself a number of times, and there are two possible orientations, just like a circle wrapping this way or that way. So this is something which we can't really draw a picture of, And so I would argue that the Solaris-like intelligence, which is essentially like a sphere, or like a ball, because it's like a planet, right, would be able, in fact, even though it's one and only, as far as it knows, it would be able to discover numbers by imagining the possibility of wrapping onto itself. And so you see, so to me, this is a good indication of two things. First of all, that the first answer that comes to mind, that, okay, so it's only one, therefore you cannot get numbers and so on, it actually may be the wrong answer. And it is the wrong answer, because, in fact, there is another way. And second, that mathematics allows you, kind of opens the door to some unexpected worlds and unexpected phenomena, which we don't even imagine, which actually could be connected to something we do, but we don't even realize it, you see. So that's the depth, and that's the beauty of mathematics that I'm talking about. You know, people ask, why do we need to know? Why do we need to learn mathematics? Why do we need to learn this stuff? I think the answer is twofold. That first of all, mathematics is now everywhere around us. All the technological advances that we are enjoying, like a laptop, like a smartphone, in the internet, etc. All the algorithms which are hidden, which are kind of secretly behind so many things and kind of secretly controlling us sometimes, I feel, they're all based on mathematics. So this is something which is very much sort of strikes close to home. But I think what's also important, and we should never lose sight of, is the kind of, I want to say, mysterious aspect of mathematics. It's a great mystery. It's a great mystery. It's a great detective story, in which we still don't know who done it, but we'd like to know. We'd like to know. That's our essence as humans. We want to know the answers. We want to understand. We want to push the veil over the unknown. And mathematics, I think, is this secret world which contains some of the most important secrets. It's a portal, if you will. It's a portal into the deepest understandings of the world, of our consciousness, of the oneness, perhaps, that we don't experience sometimes in the day-to-day life. That's why it is important. And, I love this quote also by Charles Darwin. The great Charles Darwin, of course, a biologist who revolutionized biology with his evolution theory. He said that he deeply regretted that he didn't proceed far enough to understand something of the great leading principles of mathematics. Because, he said, men thus endowed, men and women, I might say, seem to have an extra sense. So the sixth sense of mathematics. So let's try to see what kind of things we can experience with this extra sense. But I want to think of mathematics as a kind of a jigsaw puzzle. And in fact, I brought one for you. So you have a bag of these things, right? Of these little pieces. And so what you do, you just throw them. And you start to play. And you try to create out of these little pieces. Remember, Galileo said, the symbols in there are triangles and circles and other geometrical figures. So these are the symbols of mathematics. Think of them this way. Usually, however, when you get this as a present, you know what the final image should look like, right? But now imagine that you get these pieces. You get the jigsaw puzzle, but you don't get this picture. There. Try to build it, try to construct it without knowing what the final image is going to look like. That's like doing mathematics. That's like doing mathematics. And so what do you do? And of course, it's not fun to do it by yourself. It's much more fun to have a friend or a bunch of friends who join you. And you start working on it. So then what you do, you find a couple of pieces and you see that they fit. And say, oh, great. So you put them somewhere. Then you find another one which fits. And another, and another, and another. And so you're starting to build a little island around it. Whereas your friend would be somewhere here and would be building a little island here, and maybe another friend, and so on. So you're building these islands. Just like in mathematics, we have different parts of mathematics. We have number theory, which we'll talk about later in these lectures. We have harmonic analysis, another subject we'll talk about. We have geometry, and so on. And so you can see here the number theorists, working on their part of the picture. Here are the geometers working on their part of the picture. But what really makes you kind of like make a big leap in trying to understand and discern the image is when you can connect. The different islands, right? And then say, aha, so now things become much more clear, and then you can build on this. That's why in mathematics also, finding connections between different subjects, different areas of mathematics is so important. That's why we talk about unification, the idea of unification of mathematics. Understanding mathematics as this one, and realizing that it's only an illusion, that we feel that it has this many different parts. It's just our way of thinking. It's just our way of perceiving, approaching the world of mathematics. But it is actually one. So this has been a tradition in mathematics to try to find this unification. So what I want to talk to you about is about the Langlands program. So Langlands is a mathematician, Robert Langlands is a mathematician who is depicted on this picture at his office at the Institute for Advanced Study, where he is now Professor Emeritus. In this in detail, the office which you see on this picture, the office he still occupies, is the office which used to be occupied by Albert Einstein. So I sometimes, I joke, I say, well, everybody knows who Einstein is, but very few people know who Langlands is. Why is that? Why is that? So what I would like to do in these lectures is to tell you about his program, the Langlands program, and which is an attempt to unify, to find bridges between these continents of mathematics I talked to you about, number theory, harmonic analysis, and geometry. This is a theory which he initiated, and we'll talk much more in detail about this throughout these lectures. Perhaps the most important point I wanted to make here in the beginning of these lectures is that mathematics is not just this one lump of knowledge, kind of like this stuff, there's this formula, there's that equation, and so on. No, it is more like a jigsaw puzzle in which we are trying to find that image, elusive image, and we still don't know. This is the point, which, when I was studying at school, this is what I didn't realize. And I think our kids also don't realize it. So in these lectures, I will focus on three. And not because they're more important, by no means. But just as an illustration, just as an example, I would like to focus on three of them, and on the new connections, novel and exciting connections, which Langlands program is pointing us to. The first one is number theory. So it's a study of numbers, and we'll discuss in more detail what I mean by numbers. What kind of numbers? Because, there are all kinds of numbers that one could talk about. So we'll see what are the numbers here. Then another one which will be essential in this story will be harmonic analysis. So what is harmonic analysis? Harmonic analysis is the study of harmonics. When I say harmonics, here's what I mean. If you hear the sound of a symphony, if you go to symphony hall, or you listen to it on your computer or whatever, we all realize that that sound is built from the sounds of individual notes played by individual instruments. Now, each note can be represented mathematically as a wave. It is actually a sound wave, which goes from the instrument and reaches us. And mathematically can be modeled by trigonometric functions like sine and cosine. So these are the elementary harmonics. We call them harmonics. And the idea is that even though each of them is kind of simple and doesn't carry so much, but in their unity, when you bring them together, something magical can happen. The kind of superposition of those harmonics can give you, a beautiful sonata or a concert. So that's the idea of harmonic analysis. The idea that a general function or signal, a mathematician would say a function, can actually be broken into pieces which are like elementary harmonics, but now you try to do it in a more general setting. That's the idea of harmonic analysis. And then, of course, we have geometry. Now, usually when we say the word geometry, we are thinking about the geometry that we study at school. And what we study at school is the so-called Euclidean geometry. Because it goes back, it's a particular specific part of geometry, which is called Euclidean geometry, which goes back to Euclid about 2,300 years ago. He wrote this famous book, Elements, which is very important. And it is essentially the study of a plane like this tabletop, extended in all directions to infinity. So what do you have on this tabletop? You have lines and triangles and points and so on. And that's what we study at school, right? So, but now imagine that this is what was done 2,300 years ago. And of course, there are many other branches of geometry. There are many other ideas in geometry. There is also non-Euclidean geometry. Now, when people say, non-Euclidean geometry, it must be something terribly complicated. Well, it's not. It's the study of shapes, just like this basketball. It's a sphere. So instead of lines, you have meridians and parallels. And you also have triangles. They're kind of curved triangles. Kind of much more fun, I would say, than the plane geometry. No pun intended. You see? And by the way, the surface of the Earth is not flat. It's spherical. But obviously, in today's math classes, if you go to today's math classes, the Earth is still flat in there, Moreover, we learned from Einstein is that our space, our three-dimensional space we live in, or space-time, the four-dimensional space-time we live in, is not flat either. It's curved. So my point is, geometry is much richer than we usually, get exposed to. And it involves shapes like this or like this, like a torus, the surface of a donut, or whatever you want to call it, the surface of a Danish pastry or something, right? I don't know why all my references are related to food today. Okay? Any questions?
So you've been talking about those continents of mathematics that you hope to connect. Do we know they are connectable, or could some of them just not be possible to connect?
Very good question. So from what I have said so far, it may appear that we have a kind of aesthetic interest or some kind of theoretical interest in connecting, just because we want to connect. When we do the jigsaw puzzle, we do it just for fun, it's a kind of a game. But here it's more than a game. It is also because we want to solve specific problems. So in fact, Langlands came up with these ideas because he wanted to solve specific problems, which we will talk about in these lectures. But those problems seem to be completely intractable within the subject, within the continent in which they appeared. More specifically, he actually considered number theory. And in number theory, there were certain problems which which were very interesting and actually have applications, as we will discuss, but seemed to be intractable. So what he did is he was able to connect a problem of that nature to a problem in a different subject, namely harmonic analysis. So it's kind of also, you can think about this as a kind of a translation from one language to another. So what Langlands program does, more concretely perhaps, is it translates problems in one area, which seem to be intractable, very difficult, very complicated, into another language where suddenly you have a beautiful answer. And we will see examples of that, you see. So that's what I mean, sort of by, more concretely, by building bridges between different subjects. I mean actually a possibility of translating from one set of problems to another set of problems. And we already know that it's possible. In fact, I will talk about some examples of these connections which have been proved. And one of the examples is the so-called Shimura-Taniyama wave conjecture. We'll discuss that, which in fact was used to prove Fermat's last theorem, one of the most famous, if not the most famous problem in the history of mathematics, which had been unsolved for 357 years, you see. So we know they exist. What we don't know, these links, connections. What we still don't know, in my opinion, is why they exist, these links, these bridges, these connections. But finding them is not just a theoretical issue or an issue of aesthetics of kind of connecting. It actually has practical applications. We are just, if anything, we are at the beginning of this process. It's like this, really. It's like this. And we are trying to work on this. And then we have maybe built some small, some small islands. And then we're trying to connect them. So these are the areas: number theory, harmonic analysis, and geometry. And the Langlands program is a set of ideas, results, and conjectures, hypotheses, about how these pieces fit together, how they should fit together, which we still don't know, for which we still don't know the answer, final answer, even though in the last 50 years a lot of progress has been made. So this is what I would like to tell you. I'd like to tell you the story. Now, how are we going to do this? Well, first, I'm going to tell you about something which is kind of like a secret ingredient. Kind of like a secret ingredient in each of those areas of mathematics that I talked about. Number theory, harmonic analysis, geometry. And that secret ingredient is the idea of symmetry. So symmetry is something very important in mathematics, and it pops out in different branches, in different continents of mathematics, seemingly independently, but then we see it's the same idea. Kind of like what I explained to you at the very beginning about whole numbers. We naturally expect, the easiest way to learn whole numbers by counting. 1, 2, 3, 4, like strawberries, which I guess are all gone now, so it's great. I guess they're not so bad. So, right? But then there is another way by flossing, by winding. Another way to discover, which is less obvious, which is kind of hidden. Just like mathematics is kind of hidden, And that's a very common occurrence in mathematics. The same concept, the same idea would have different manifestations. It would have some more obvious manifestations from a particular point of view, but then some less obvious. And so it is with symmetry. But the fact of the matter is that symmetry, this concept, this idea of symmetry, appears in all of these continents, in all of the subjects of mathematics that I talked about, in more obvious ways than in others. And this would be, for us, the first indication that these areas are actually connected to each other, because they share this secret ingredient. They share this particular idea, this particular theory, you see. And it's kind of built, you can say that, what is the most important concept in the Langlands program? And I think it would be fair to say that symmetry is the most important concept. So that's why I would like to start with this idea of symmetry. What symmetry is, what mathematicians understand by symmetry, what can you do with symmetries? Okay? Now, when I ask someone, what is symmetry? What is symmetry? People usually give me examples. Like, what do you think of when I say symmetry? And one of the first ones is usually a snowflake. We find a snowflake to be symmetrical, right? Or another one, which is quite common, is a butterfly. Kind of the two wings are kind of the same, right? Or people think of the human body as being symmetrical. It's depicted on a famous painting, a drawing by Leonardo da Vinci. Okay? But so what does it mean? What does it really mean? What are the symmetries? And so what I would like to illustrate, the way I would like to illustrate this, is by using bottles, which, by the way, today is incredibly important because it's so hot, and so you have to stay hydrated, you know. So I actually brought 2 bottles because I thought it wouldn't be enough. And they just happened to be very good for making this point. So one of them is round. I stripped them off all the labels, which was not easy. And the other one is square. So now I want to ask you, each and every one of you, which one of them is more symmetrical? Okay? So let's do a vote, okay? Just to make it more fun. Okay, those who think that the round bottle is more symmetrical, please raise your hand. Okay. All right, and now those who think that the square bottle is more symmetrical, please raise your hands. Okay, well, at least there is at least non-zero number of people, well, who try to supporting the underdog, right? So, okay, now what do? We have to give an argument. We have to give a proof. And so here's the argument. Here's how I would argue that indeed the round bottle is more symmetrical. That we call such transformations symmetries. A symmetry is a transformation which preserves the shape and position of an object. I will say, let's look at the transformations of this object that preserve its shape and position. So here is a round bottle. And I'm thinking, what can I do to it? What can I do to it so that it does not change its appearance, you see? And it's easy to realize that any rotation of this bottle, any rotation at all, about the central axis, or like imagine like a vertical axis going through this bottle, by any angle at all, would not change it. What do I mean not change it? So let's suppose you turn away, right? And I do this, and you look back, right? You won't know the difference. I mean, there's some dimples here, but okay, let's ignore that. So, right? So that's what I mean by that. Now, if I look at the square bottle instead, we'll see a totally different story. If I turn it by a random angle, then you would know the difference, because it would change its position. However, if I turn it by 90 degrees, or 180, or 270, it will not change its position. So, these are the transformations that I'm interested in. And we see that for the round bottle, arbitrary rotations will do. For the square bottles, only 4 rotations will do. The multiples of 90 degrees. 90 degrees, 180 degrees, 270 degrees, and 360. Also because actually we'll come back to, like every point will get back to its original position. So yeah, for sure, that will not change it either. So what do we find? We find that the round bottle has, as symmetries, all possible rotations by all possible angles, whereas the square bottle only has 4 by 90 degrees, 180 degrees, 270, 360, right? So which one is more symmetrical? Well, the one which has more symmetries. One has infinitely many symmetries because there are infinitely many possible angles from 0 to 360 degrees. And the other one only has 4. So surely the round bottle has more symmetries, therefore it's more symmetrical. So that's the argument. Now, the conclusion we reach here is that the round bottle is more symmetrical than the square bottle. But if you are a mathematician, you don't stop here. So this is the point. So you make the next step. So you see, this is already quite good, because there was a question which was kind of posed. It was not quite clear what it is meaning. Intuitively, we felt that the round bottle is more symmetrical. And now we have a conceptual explanation, which is nice. But this is not yet mathematics. This is not yet mathematics. Mathematics begins when you then make the next step and say, let us look at the symmetries of a given object, at the collection of all symmetries of a given object, such as a round bottle or a square bottle, as an object of its own, as an object of itself, you see. That's when we start doing mathematics. So we look at all symmetries of a given object. And so, for instance, round bottle, and then we can ask, can we actually think of them as something geometrical, a geometrical entity? The set of all rotations. Anyone? What do you think that is? The collection of all possible rotations. Yes?
Translational and rotational.
Rotational. But what exactly is the set, right? So, okay.
0 to 2 pi.
0 to 2 pi. Okay. But how do you can you visualize it? Can you imagine it as something?
A circle.
A circle. Very good. So this is exactly the right answer. Good job. A circle. So the set of all symmetries of this particular object, namely the round bottle, is a circle. And you see, this is already mathematics. Because out of thin air, literally, you have come up with an object. Right? Which actually has nothing to do, it has obviously something to do, but it's not a real object in the sense that we don't find it around us. This circle, I drew it on this slide, right? I drew it on the slide, but it's not an object like this jigsaw puzzle piece or like this bottle or like this bottle. It's something which exists in our imagination, in our mind, in our consciousness, right? It's an abstract object. So, likewise for the square bottle. But for the square bottle, there will be just a set of 4 points. Just this set of 4 points, which you can think of them as the points where this one specific point, on one of the points on the edge of the bottle, would be sent under this rotation. So we have created 2 mathematical objects out of our bottles. One is a circle, and the other one is a set of 4 points, the corners of this picture. And there is more. So we could stop here, and it's already interesting, because we have already created something that we could study abstractly, mathematically. But then once you create that object, which we have done already, you start wondering whether it has any hidden structures, whether it has any particular things that we can do to points of that object. And we realize very quickly that actually there is more, because if I rotate this bottle by, let's say, 30 degrees, okay, it doesn't change its position, so fine, it's a symmetry. Then I rotate again by 20 degrees. The net result of these 2 motions, the net result of these 2 operations is rotation by 50 degrees. So it means that I can apply these motions, these transformations, back to back. That actually, given any 2 points on that circle, we can produce a third one by simply applying the 2 transformations back to back. Mathematicians call that composition of 2 transformations. Composition means applying back to back. In the case of a circle, it's just the addition of the angles, clearly, because each point on the circle, as I explained, each point of the circle is, of course, just a particular angle from 0 to 360, or if you prefer, from 0 to 2 pi. And if you have 2 of them, 2 such points, you have 2 angles, and you can add the 2 angles together. And you obtain a new angle, you see. So that's the structure. And now we have arrived at the concept of symmetry, symmetry group. And this is one of the most fundamental concepts in all of mathematics. And this is that secret ingredient which I mentioned, which appears in all of these continents of mathematics that we will be discussing here. Right? But now the point is, you see that this is actually bigger than the original bottles. Because, see, I have another bottle. Yet another bottle. And see, the funny thing is that these 2 bottles are different. As you can see, for example, I've drunk more water from this one than from this one. Right? They're different. But they share a group of symmetries. And that's the beauty of it. That's the universality of mathematics that I mentioned earlier. That the same circle, the same group, the same circle kind of services all round bottles in the world. Every round bottle in the world has the same group of symmetries, the circle, as does every round object. You know, like it could be a round table, it could be round glass, it could be round column, etc. In fact, roundness, what does it mean to be round? To be round means to have the circle as your group of symmetries. So that's the takeaway from this. But, and likewise, the square objects are, of course, the ones which have the group of symmetries of rotations by 4 angles. So that's the notion of a square object. Now, just so you don't think that these are all possible groups, a circle and 4, I want to give you one more example, which is a group of permutations. And here I want to use another food prop. Namely, so we've run out of strawberries, but I have some tangerines. And so you see, by the way, the secret to healthy life is eating fruits and vegetables. Since there are many students here, I feel like I should share some wisdom. Okay? So, you see, if I have a number of objects, I can talk about permutations of those objects. So, for instance, well, I cannot really show you you cannot see from the top, but maybe. So permutation means that one of them goes to the position of another, and likewise, for each of them, you permute them amongst each other. Maybe it's better to show it to you on a blackboard. So let's say if you have 3 objects, 1, 2, 3, and then you have a permutation would be a particular way of assigning where the first one goes, then where the second goes, and where the third goes. So for example, we can say the first one goes here. Then we ask, where can this guy go? But we don't want it to go to this one because this one is already taken. So a permutation is such a transformation for which no 2 objects go to the same thing. No 2 elements go to the same thing. So that means that this guy can go either here or here. Okay? So let's say it goes here. Then we ask, where can this one go? Well, it can't go to this one, right? Because it's already taken. It can't go to this one, it's already taken. It can only go here. So that diagram represents one permutation. And in the case of I could show it to you by using my tangerines. So you have three tangerines. So let's say this is 1, this is 2, and this is 3. Then I just exchange 1 and 2. And the third one stays the same, right? That's what it is. So here I have those 3 objects, and I'm actually physically doing the permutation. On this picture, I'm showing what the permutation does by marking them here where they were before and showing where they go under this permutation, under this motion, under this transformation. Now, how many such transformations are there if you have 3 objects? Well, let's see. The first one has 3 possibilities. It can go to first, to second, and to third. Right? So there are 3 options. Once I choose where it goes, for example, goes here, I can discuss how many options the second guy has. Now, how many will it have? Well, this one is already taken, so there are 2 remaining. And it will always be like this. And then, for this one, there is only 1 option. So 3 times 2 is 6. And likewise, if you have 4, 5, and so on, you will have, if you have n objects, 1, 2, 3, n, there will be n times n minus 1 times n minus 2, and so on, times 2 times 1 possibilities. This is what's called n factorial. For now, I just want to say that there are 6 such permutations. So the group of permutations of 3 tangerines, or 3 objects, 3 elements, has 6 elements. So you see another illustration of the fact that there are more symmetries, there are more permutations than the number of objects themselves. There are 3 objects, but there are 6 possible permutations. By the way, you can think of permutations as symmetries of this set. If you imagine that all of these tangerines are kind of the same, a symmetry of this collection of tangerines would be any motion I do, under which they will look exactly the same. So that would be, this motion, and so on. There are 6 of them. But I would be remiss if I did not explain what is the operation. Because a group is not just a collection of things. It's not just a set. A group is a collection of things together with an operation, which is applying back to back. So, but that should be clear from this picture, because let's say I do one more. So let's say now this one goes here. And then this one goes here, and this one goes here. So this is a permutation, and this is a permutation. And as I promised to you, in a group, given any two elements, you can obtain a third. So what will be the third? The third will be a permutation which you obtain by tracing these arrows. Under this permutation, 1 will go to 2, then to 1. So the net result would be it will go to 1. 2 will go to 1, then to 3. So the net result would be to go to 3. And 3 would go to 2, you see. So that's a new permutation which is obtained by combining or by adding together these first two. Just like two angles can be added to each other to obtain a new element of the circle group and so on. Okay? So these are just the first few examples. And what I want to finish this lecture with is by summarizing what we have done so far. So far, we have discussed the secret ingredient of the three continents of mathematics, which will be our main interest in these lectures. Our main interest in this lecture will be number theory, harmonic analysis, and geometry. And all of these continents of mathematics, all of these areas of mathematics share one thing, which is that symmetries play a very natural role in them. And so far, we have discussed how symmetries appear in geometry, because obviously we talked about rotations and things like that. So these are the things of geometric nature. But I don't want you to think that this is the only way that symmetries appear. It is like thinking of appearance of numbers, whole numbers, through counting. It's only one way. There are other ways to come up with numbers. And likewise, there are other ways to see the appearance of symmetries. And what we will discuss in the second lecture is the appearance of symmetries in number theory. And then, later on in these lectures, we will also talk about the appearance of symmetries in harmonic analysis, as well as in quantum physics, where we will see that symmetry groups actually play a tremendous role in our discoveries, in physicists' discoveries of the fundamental blocks of nature. I will talk about the appearance of symmetries in the discovery of quarks, and quarks being the small pieces of constituents of protons, neutrons, and other elementary particles, or rather I should say particles which had been thought to be elementary but turned out to have those constituents inside. And that story is a beautiful story of application of mathematical ideas of symmetry as well. And it is through understanding the symmetries, somehow the symmetries would weave these connections between these continents of mathematics, and this will be our way to understand the Langlands program. All right, great. Thank you so much, and I hope you come back for the second one. It will be even more fun. Thank you very much.